All right, y'all. I'm going to give you a couple minutes to take a look at this jog your memory question. This is one of the harder salt solution questions, so that's where we left off on Tuesday, which feels like a lifetime ago. We were talking about how do salts change the pH, if at all. Maybe they don't, but in many cases they do. So we are looking at disodium citrate, and I've also given you a picture here of what we're working with. All right, and I want to know, is this going to be an acidic, neutral, or basic solution? All right, so take a couple minutes, write out, what does this thing do? What does that salt do in solution? What's your cation? What's your anion? Why do you have Ka values? What are we supposed to do with those? So, like, brush the cobwebs off, open up Tuesday's notes, talk to the person next to you, get your mind back into 1220, because I assume you didn't spend most of your break thinking about it, so get your mind back into chemistry. All right, hopefully you wrote something down. So let's figure out what's going on in this question. Okay, we're dumping this thing into solution. All right, so our first step is to say, well, how does that break up? Okay, so we're going to have two Na pluses, and then we'll have this big organic thing, C6H5O7H 2 minus. I know it's got to be 2 minus because my salt has to be neutral. I've got two sodiums on there, both carry a +1. So then this thing must be 2 minus, all right? In other words, it must have lost 2 protons from its fully protonated version. So that's citric acid. So here's citric acid where it's fully protonated, and I've split it up so that the protons, the hydrogens that are likely to come off or that are acidic, are here. That's why we have 2 chunks of protons. Those H5s, those don't come off. But those 3 H's, those are likely to come off, which is why I have given you 3 Ka's. Okay? So Ka1, we would use that to describe the likelihood, the likelihood of the first proton coming off. Okay? So that first H3, C6H5O7, what's the likelihood of that becoming H plus and H2C6H5O7 minus? Let me move this around just a touch. All right. Okay, so that's Ka1, but we didn't put in citric acid. We put in the disodium salt. Okay, so we don't need Ka1. We actually need Ka3. Okay, so I'm looking at this. Let's write this out. Let's think about what is that doing. And what's happening is this is what we called amphiprotic. All right, it is negatively charged. So it can act as a base, which is usually what anions do. Okay, it's got some negative extra lone pairs. It could grab a proton and make some OH minus, but it also has an acidic proton left, so it can do both. So that's what we need to acknowledge, is that it's amphiprotic. So when it acts as an acid, here it is losing its final H. So we'd have C6H5O7 3 minus plus H plus. That is the loss of the third proton, which is going to be described with Ka3. Okay, so to describe this, and really what I should do is I should draw this as very long equilibrium arrows. Okay, so this is Ka3. Okay, that describes the balance of that anion losing another proton, its last proton. But it can also be a base, so let's describe that process. Okay, so it could also be a base. Okay, so with water, because it's got to have water to take a proton from, it could grab a proton and become C6H5O7H2 minus, right? Because it's gaining another proton from water, which would mean it's generating a little bit of OH minus, so it would be a basic solution. We need to describe this equilibrium. Okay, we don't have any KBs though. I need a KB. This is a base reaction. Okay, so how do I relate KBs to KAs, right? Well, I know that the Ka of this is my Ka2. That's the likelihood of the second proton coming off. So I can write Kb2 as Kw over Ka2. And we have that right here. So that's going to be 10 to the minus 14th divided by 1.7 times 10 to the negative 5th. That number is 5.9 times 10 to the negative 10th. We know Ka3, that was 4.0 times 10 to the negative 7th. Okay, so both are small numbers, right? So in both cases, reactants are favored, but my Ka is 3 times, like 1,000 times larger, right? 10 to the minus 7th is a much bigger number than 10 to the minus 10th. So this is an acidic solution for this reasoning. Because my Ka is bigger than Kb, it's acidic. This is a challenging question. Okay? This is like one of the hardest questions I think you will see, or could potentially see on the exam. So I just did another one of I had this on my post-lecture exam questions, and I just did my answer videos for those, so I'm going to get those up later today. So if you need more practice, there is more practice to be had. Okay? Questions? Yeah, go ahead. So when this acts as a base, I am not going to take Ka3 to do it, because that would be asking about the conjugate base of that. That would be the C6H5O7 3 minus. That would be the 3 minus that I'd be asking about. But I want to know about how that anion acts as a base, and so I need to know its conjugate acid, which is my Ka2 value. That is what I think the most common error would be to make the Kb equal to Kw over Ka3. That would be the mistake that I think is most common. Don't do that. Yeah. Notice that Ka1 is always bigger than Ka2, is always bigger than Ka3, right? It's harder and harder to pull off a proton as you deprotonate. Okay, so that was something we learned from chapter, what was on the past exam. See that my numbers are getting smaller, Whether or not this is going to be acidic or basic is going to depend on those, like the jumps, like how much smaller between those two. All right. So that is our jog your memory for today. We also talked about acid structure, and I put a bunch of those questions on your recitation sheet for this Friday. So you'll see some of that, but that was the other thing that you probably forgot about over the weekend, over the long weekend. So just as a heads up, that also exists. And now we drive on into chapter 17, all right? We are going to stay, this is still all acid-base equilibrium, but we're going to make the solutions a little bit more complex. Yay. All right. So we're starting with the common ion effect, all right? Chapter 16, weak acids and weak bases. We acknowledge that we had to use Ka and Kb because it was an equilibrium. It didn't 100% dissociate. All of those questions were like, hey, you put in just the weak acid, or you just put in the weak base. Now in these questions, we are going to add something else to the solution, okay? And in particular, we're going to add something with a common ion. Right? So we're making more complex mixtures because we're going to add in more than one thing into our solution. All right? And it's a common ion. So we're going to start by looking at this weak acid equilibria here. HA breaks up into H plus and A minus, okay? We were just starting with only HA. And now we're asking ourselves, well, what if we added in something that had H plus, or we added in a source of A minus? So that would be adding a strong acid, right? That's our source of H+. Or what if we added in a salt of A-, right? We can't just add an A-, it would have to come as like sodium A- or Na+, A-. We'd have to package it as a salt. If I add one of those two things, that is adding a product to my reaction, right? I'd be jacking up one of the product concentrations. We know if we increase this, we shift the reaction back towards our reactants. This is just an application of Le Chatelier's principle. You've already seen that, okay? This is a familiar subject just packaged for acids and bases. If we are looking at a weak base, okay, we generate BH plus and OH minus. Those are the ions, right? When I say common ion effect, I'm saying, well, what if I added one of those ions in? So I could add a strong base as my source of OH minus, right? Or I could add in a salt of BH plus. So that might look like BHCl, right? So I'm generating a bunch of this. I'm putting in product. I'm going to shift the equilibrium back towards the reactants. So if I add a common ion, I am going to wind up with more of my weak acid or weak base. Okay? That's all. This is just an application of Le Chatelier's principle, but then we package it in, I think, unnecessarily complicated language. But this is what it is in your book. All right? Whenever a weak electrolyte, so that a weak electrolyte would be our weak acid, so like HA, or our weak base. So whenever a weak acid or weak base is mixed with a strong electrolyte, so a strong electrolyte would be a strong acid or a strong base or a salt that completely dissolves. All of those generate a bunch of ions. That's what an electrolyte is, a strong electrolyte. And if they contain a common ion, then the weak electrolyte ionizes less. In other words, we generate more of it, okay? So we're going to have more of the B because it's split up less because I just added in a bunch of the products, okay? Or I'd have more HA because I had to shift left because I just put in a bunch of products, okay? Again, this is just Le Chatelier's principle applied to base and acid solutions. So let's just jump right into a practice problem. I'm looking at 0.1 moles of acetic acid, and I'm mixing it with 0.01 moles of sodium acetate, and I bring it to 1 liter with water. What's the pH of this solution? All right. I have a comparison point here. When I haven't added any of the acetate, I know the pH is 2.89 for that 0.1 molar acetic acid. As a side note on language, when you see ic acid, that is telling you it's some carboxylic acid, okay? When you see some, like, here's our metal, but then the 8 ion, that is its conjugate base, okay? So ic acid is telling us that we have that carboxylic acid functionality, right, that we looked at on Tuesday. And then the 8 is when it's deprotonated. Okay, just so that linguistically, if you see lactic acid and sodium lactate, you are now seeing those as a conjugate acid-base pair. All right, so let's set this up. We're gonna stick with our ice tables, so don't worry, ice tables aren't going anywhere. So CH3COOH is gonna split up into CH3COO minus. That's just our acetic acid and acetate anion and some H+. Okay? In all of our other questions, we were starting only with this 0.1 molar of our acetic acid. But now, my initial value also has some CH3COO minus. Okay? So I'm starting with a value there. That's the only difference. I have a number there now. Okay, we're still imagining that we don't have any H+. I haven't calculated any of it. So in my change, I still have to make some products, right? I cannot have a negative amount of H+. So I've got to be adding some products. So I have minus X, and plus X. So now we have our equilibrium values. And we are going to continue using our 5% assumption that X is going to be a very small number. Ka is still a very small number, right? Which means that we're not going to see much change. So I'm going to have 0.1 and 0.01. So I can set up a Ka expression. 1.8 times 10 to the negative fifth equals 0.01. That's my CH3COO minus times X over 0.1. Now I just solve out for X. All right? X in this case is 1.8 times 10 to the negative fourth. That is my H+ concentration. All right, so let's take stock of what just happened. All right, well, 1, that is way smaller than my 2 values in that table, so I'm feeling good about my assumption. Okay, X is way smaller than 0.1 and 0.01. I know that I'm going to, now I can calculate a pH. Okay, so pH for this is going to be the negative log of that value. And that's 3.74. Okay. So 3.74, we have added in some of our conjugate base, and our pH has gone up. So that makes sense, right? Our pH has increased. We've added in a base. So we have less H+ than we did before, which must mean that our CH3COOH has ionized less, right? That is our source of H+. If I have less H+, then I must have dissociated less, or I must have ionized less, okay? So this is a very common question, to see on the exam. What is the pH of this system with both the acid and its conjugate base? All right? Now you get to practice. All right, so try this question on the fluoride ion, but now you are adding an HCl. So I want you to first stop and ask yourself, what's the common ion? Which one is the weak electrolyte? And then calculate, I'm not asking for pH, notice, I want to know the fluoride ion concentration. So you're still going to set up an ice table for this. All right. This is a slightly twisted question from what we looked at, in that our common ion is now the H+. All right, because this is my weak electrolyte. HF is a weak acid, so I'm going to consider it a weak electrolyte. It only partially dissociates, right? And it dissociates based on that Ka. HCl is a strong acid, and so I'm going to get full dissociation, 100%. So all of it will be H plus and Cl minus. And so that's going to be the strong electrolyte. When I put in H plus, when I put in HCl, it totally dissociates. So this is going to tell me my initial concentration of H plus in solution. All right, so I'm still going to set this up with an ice table. Cl minus is floating around in solution, but it's a spectator ion. It doesn't do anything. Remember, it doesn't want that H plus back. It's happy as Cl minus, so we leave it alone. Okay, so I'm starting now with 0.20 molar, right, of my HF and 0.10 of my H plus. But I don't have any F minus, right? So I got to make some F minus. Die. So I need to make some of that. All right, this is looking very similar to our problem from the last slide, except for now my X is going, I'm really thinking about that F minus, that fluoride, because I'm going to assume X is much smaller than my 0.2 and my 0.1. So I'm going to make that assumption as well. So this is really 0.2 and this is really 0.10. Okay, so Ka, we get that, is 6.8 times 10 to the negative fourth. That's 0.10 times X divided by 0.20. So I'm going to solve out for X, which is my F minus concentration. That was 0.012, nope, that's the wrong number, 0.00136. And that's my F minus concentration. That is much smaller than 0.1 and 0.2. So it also means that when we go to calculate the pH, I really don't care about the small contribution from HF. The pH of the solution is pretty much entirely dictated by the fact I just dumped in 0.1 molar of HCl, right? That's a lot of strong acid. So to calculate the pH, I'm just going to take the negative log of 0.10. That's all I need, right? I don't care about this little bit of extra H plus there. That would give me the same value. Okay, so I have a pH of 1, it's very acidic. And then the other thing I want to point out is if I had not added HCl, if it had just been HF, okay? So just HF in solution. I went through and did that ice table, okay? So I wound up with Ka, okay, so that's 6.8 times 10 to the negative fourth equals X squared over 0.20. All right, that was without adding in any of the H plus. So if I calculate out what is that X value now, which is my F minus, that was 0.012 molar. Okay, that's where I was about to write that other number. So now compare, okay, those two. That's the comparison I want you to make. When I put in the strong electrolyte, right, I have a lot less of that F minus because I am making more HF. Okay, when I add in the strong electrolyte, our weak electrolyte ionizes less. And I see that when I compare the two F minus values. Okay, it's a lot smaller when I put in that H plus. Okay, so that must mean that I've generated more HF in comparison between these two solutions. All right. Here's a conceptual question. I just wanted to give you this flavor as well. So when NaCN is added to a solution of HCN, what happens to these concentrations? So I'm asking, when I put that sodium cyanide in solution, what happens to HCN? What happens to H+? And what happens to the pH? Okay, so the first step would be write out the equilibrium we're talking about. Okay? Identify to yourself, this is a weak electrolyte. That's a strong electrolyte. And then say to yourself, this is a common ion question. All right, so let's go 1, 2, 3. All right, when I put in Cn minus, when I put in that sodium cyanide, what happens to the concentration of HCN? Does it increase, decrease, or stay the same? Good. It increases. If I put a bunch of this in, if I increase the amount of my product, I am shifting over this direction, right? If I increase Cn minus, that must mean to maintain the same Ka value, I have to make some more HCN. This is Le Chatelier's principle. You put in products, the system responds by taking some of those products and making reactants because it has to rebalance. Okay, so I'm going to increase my HCN. So what happens to my concentration of H+ when I put in Cn minus? Does it increase, decrease, or stay the same? Imagine it is a week from Friday. You might as well answer. You're on the test. You should take a guess. I am going to see it decrease. Okay, if I put in Cn minus, I have to make some more HCN. That requires the consumption of H+. If I put in Cn minus, if I'm going to make more of that HCN, I have to consume some H+. Okay, so I'm going to see a decrease in my H+ concentration. Also, you could also think about it as you're just adding in a weak base. You're adding in a base. That's a base. It's going to consume. In my mind, I am saying it's going to eat some of the H+. So it's going to go down. What happens to our pH? What happens to the pH when your H+ concentration decreases? It goes up. Don't confuse yourself on that one. We will see an increase in pH. The other way of thinking about it is, again, we added in a base. We should see an increase in the pH. Okay? All right. That's the common ion effect. And the good news is, the whole next section is all about the common ion effect. We're just going to call it something different, all right? So we can use what we just learned as we dive into buffers, all right? Here's my premise for buffers. Why do we care about them? We've made the pitch that pH is a really important chemical feature of a system, right? We need to know what it is, all right? It's particularly important in biochemical systems, right? So like all of your enzymes evolved working at pH 7, unless maybe you're thinking about something that was in your stomach, in which case it's got to work at around a pH of 2, right? But your enzymes start to fall apart as the pH changes. So they wouldn't work very well. In other words, the pH of your blood is incredibly important. If it changes, you will get very sick. So we don't want the pH of our blood to change, because if it did, then we would fall apart. So we want our blood, we want these systems to be buffered. We want them to resist changes to pH. That is what a buffer is. It resists changes to pH. Okay? So that's our first definition that I'm going to write down for ourselves, that a buffer, by definition, is a solution or solutions that resist changes to pH when an acid or base are added. So even though we're adding in some acid or base, the pH of the system doesn't change because it is buffered, okay? That is our sort of generic broad definition of a buffer. Chemically, let's ask ourselves what a buffer is. Okay, so I might also define it as a solution that contains high concentrations of a conjugate acid-base pair. So that might be, it's got to have a high concentration of HA and A minus, or I could be looking at a weak base and its conjugate acid. But I have to have meaningful, significant concentrations of both components. That's the chemical definition requirement for a buffer. You got to have both, and you got to have a lot of both. All right. So now let's try and unpack why that works. Why does a system with those two components, why does it resist changes to pH? All right, so we have a solution. We're looking at this combination of HA and A minus, and we add some OH minus to the solution. So what happens? All right, so if I put in OH minus, what will happen? Let me see where my next line is so I don't write over it. Okay, HA will react with my OH minus. My weak acid swoops in and is like, no, we're not going to increase the concentration of OH minus. I'll take that and I'll convert it 100% to A minus. So we add in a strong base, we add an OH minus, but because we have HA there, we convert it to A minus, a weak base. Okay? So we neutralize it. Okay? If I put in H plus, I have A minus there to do the same thing. Here's my weak base. Saying, no, we're not just going to spike our H plus concentration, we're actually going to make some HA. So instead of dumping in a bunch of H plus, we generate some HA, which actually is a weak acid and dissociates a very small amount. Thus, we have a very small change in pH. So OH minus reacts with our HA, and H plus reacts with our A minus. That's why we need both in there, because we want to resist changes in both directions. Okay? Your book has a nice visual of what this would look like. Okay? So here's our starting concentration. We have both acetic acid and the acetate anion. All right, so this is our buffer in the middle, and we add OH minus. Okay, so we consume a little bit of our acetic acid, right, and we make a little bit of our CH3COO minus. Okay, that's its neutralizing OH minus. In the other direction, our acetate anion consumes that H plus, and we wind up with a little bit more COOH, or our acetic acid, than we did before. Okay, so this is our neutralization in either direction. We're not just dumping in H plus and OH minus, we're then reacting it with the stuff that we have in there. All right, so we want to be able to do, well, here's the point I want to make. We want to be able to make these things first. Right, so it's not just any weak acid and weak base that you put in there. They have to be a conjugate acid-base pair. Okay? We have to put in HA and A minus because these are at equilibrium, right? They're constantly reacting with each other. Yes, HA is going to react with A minus, but then we're going to go back in the other direction, and we have a constant concentration of both. So it can't be just arbitrary, you can't just throw in any weak base and any weak acid. They have to be the conjugate acid-base pair. Okay? Otherwise, it doesn't work. And if we want it to be really good at resisting pH in both directions, the ideal mixture is where we have a 50-50 or equal amounts of HA and A minus. So that was how the graphic showed it on the last slide, where we're starting with the same amount of HA and A minus. So in either direction, we can resist change. Okay. We're going to want to calculate the pH of these buffers. All right, so we're going to start with the same old acid dissociation reaction. We're going to write Ka. And at this point, hopefully this is boring and be like, yay, I know this, okay? I want to find the pH of this system. So what I'm going to do is I'm going to take the negative log of both sides. Okay. So I'll have negative log of the Ka equals negative log, and I'm going to do it of this whole chunk. Okay, and remember, I'm trying to get the pH out. Okay, so I'm going to split this out. One, I'm going to recognize that that is the pKa, just the negative log of the Ka is the pKa. Okay, and I want now to isolate that negative log of H+. So I'm going to have pKa equals the negative log of H+. Okay, and then I'm going to split this out, so plus the negative log of A minus over HA. And there's my pH. Okay? With one more rearrangement, I'm going to bring that second term over to the other side. So I can now say that the pH of a buffer, and notice I'm calling this a buffer because I have meaningful concentrations of both A minus and HA, is equal to the pKa plus the log of that ratio, of the ratio of the base to HA, to the acid, okay? So this is a friendly equation called the Henderson-Hasselbalch, and it helps us avoid ice tables, okay? All right, so we're carrying that on into the next slide. And there it is. pH pKa plus the log of the base over the acid. All right? This only works if you meet the 5% rule, okay? If we have a small change in our ice table, which for buffers we almost always do. So if you see a question about a buffer, it is a good bet, if it's quantitative, that you can just jump right here. Okay? So this is the thing. We like this. Okay? It makes your life easier. So let's try it out. All right, we're going to look at a buffer. We've made a buffer. I've taken 0.12 molar of lactic acid and I've combined it with 0.1 molar of sodium lactate. Okay, so again, there's our ic acid and the 8 there. That's telling me it's a conjugate acid base pair. And I've been given Ka for lactic acid. We're going to work it in the way that we have always done it, with an ice table, and then we'll compare it to the work that we've done with the equation that we just learned. So I've split this out, the negative log, and I have A times A in there, and so I split, like A times B, right? Our log rules would be log A plus log B, but then I am applying that negative sign in front to both. And I'm now bringing that term over to the left side, so I'm going to add that to both sides. All right, so let's see it in action. We're going to start with our ice table. Okay, I'm going to call this HL, and I'm going to call this L minus, just because who wants to write out full names? Okay, we're doing this our standard ice table style, all right? But now, again, this is a common ion question. I have more than one thing to start with. I've got HL, which is 0.12. And I've got L minus, which is 0.1. Okay, and I'm solving for this H. I want to know what this H plus is. I'm going to lose some of this. Gain some of my products. And I'm going to use my assumption, which again I think is good because these are pretty large concentrations, relatively speaking. Okay, so Ka equals X times 0.10 divided by 0.12. We're given that value, that's 1.4 times 10 to the negative fourth. I can solve out for X, and X equals 1.68 times 10 to the negative fourth. That is my H plus concentration in molarity. I take that, I put it into the negative log. pH equals the negative log of that value. pH of this solution is 3.77. That is our ICE table. We just did that for our common ion effect. All right, but now we're going to try the Henderson-Hasselbalch equation. Okay, and make sure that it works. Okay, as a side note, yes, we did pass our 5% rule. Look at that's a much smaller number than 0.1 and 0.12, so we passed our assumption. And now we can say pH, let's do it this way. pH equals pKa plus the log of A minus over HA. All right, the pKa is just the negative log of Ka, so that's negative log of 1.4 times 10 to the negative fourth. That equals 3.85. So the pH equals 3.85 plus the log of 0.10, my L minus, divided by 0.12. That's 3.77. Okay, so once you have concentrations and a pKa, this is a fast question. Okay, and we've proven to ourselves we get the same answer. This is just making the math nicer for us, for when we are dealing with a buffer where we have meaningful concentrations of these two things, of A minus and HA. Yeah. Yes, because X is so small that the change is going to be very small. All right. So this would be like your base question on the exam, like my easiest way of phrasing it, or our easiest way of putting it to you. And now I'll turn the screw, I guess. So here is a question for you. What is the pH of a 0.87 molar NaHCO3 and 1.45 molar Na2CO3 solution? So now I've taken a buffer question that you should be able to do with, this is a Henderson-Hasselbalch question. The twist is it's polyprotic and you gotta pull the right pKa value. So take a look at this one. Think about what you're putting into solution with these two salts, and then start plugging in some numbers into your Henderson-Hasselbalch. Okay, so take a minute to do that. Actually, and I'm going to expand this. I'll say to the base, and this is the acid. Okay, so how does HCO3 minus relate to CO3 2 minus? And which Ka value are you going to use to calculate your pKa? Okay, those are the two twists. throw it. So this is sodium bicarb and sodium carbonate. I've got a bunch of Na+ floating around. But again, I picked this because I also want to keep like sneaking in these salt questions in there because you're going to see salts on the next exam too. So we might as well talk about them throughout. I'm making HCO3 minus here. Okay, that's what that salt is going to contribute to solution. Yes, Na+ is in there, but it's a spectator ion. I don't care about it. Like, just ignore it. Okay, here I'm making CO3 2 minus. How are these two related? Right? When HCO3 minus acts as an acid, okay, it becomes H+ and CO3 2 minus. So I should label HCO3 minus as my acid and my CO3 2 minus as its conjugate base. Okay, that's how I am going to decide where to put these numbers in this part of my equation. Okay, that 0.87 molar, that's my acid concentration. Okay, so that's that piece solved. Now for the pKa, which one to take? Again, this is my acid. It's thinking about the removal of the second proton. So I'm going to take the negative log of Ka2. Okay, so that's the negative log of Ka2, right? This is the thing that describes the likelihood of that second proton coming off. That 2.5 times 10 to the negative 4, that's if I had added in carbonic acid, H2CO3. I didn't add in carbonic acid. That was not in this. I didn't put that in, so I'm not going to even think about it. Okay? So the negative, my pKa that I need to use for this is 10.25. Okay? So my pH equals 10.25 plus the log of 1.45 over 0.87. And that gave me 10.47. Okay? A place that you can sort of check yourself. Okay? This number, the pKa, is the value when you have equal amounts of your acid and base. Okay? That would be if my log was of 1, where it was equal. But right now I don't. I have more of my base than of my acid, so I should see a slightly elevated pH. Right? This is a little bit more basic than that. That checks out. That makes sense to me. So keep doing those reality checks to say, like, does my answer make sense? All right, the other thing we could do in these questions. Okay, so here's a practice problem. How many moles of NH4Cl, ammonium chloride, must be added to 1 liter of 0.1 molar NH3 to form a buffer whose pH is 9? Okay, assume no change in volume when ammonium chloride is added. And I tell you that the pKa of NH4+ is 9.26. This is a Henderson-Hasselbalch question. I'm just not asking for pH. I'm asking for one of those concentrations in the parentheses. Okay? So this is just another way to twist the question. All right, so I'd be setting up, and again, as soon as I see the word buffer, I'm like, I am going to the Henderson-Hasselbalch equation. That's usually a good bet. So I want the base on top. The base is NH3. The acid is NH4+. I am wondering what that concentration needs to be. Okay? So I know that the pH is 9. That's my desired pH. I want that to be true. My pKa is 9.26 plus the log, and I know that I'm starting with 0.1 molar of NH3. And I'm going to solve out for this last little piece down here. What is that value of NH4+ that needs to be added? So I'll do some math. I'm going to have negative 0.26 equals the log of 0.10 over my NH4+ concentration. So I have 10 to the negative 0.26. I'm just getting rid of my log. And I find that my NH4+ concentration equals 0.18. And that's molarity. And then I say, hey, nice, I put it into 1 liter, so that is also the number of moles that I need. which would also be the same number of moles of ammonium chloride because it's a 1-to-1 ratio. Every unit of NH4Cl puts in 1 unit of NH4. Okay, so that's the other question, the other quantitative thing I could ask you about these buffers. All right. All right. So that's the Henderson-Hasselbalch. Let's look at two more things that you need to know. Well, there's a couple more, but I need you to know how to make buffers. All right. There's two different ways to do it. All right, we can just straight up add in the acid and its conjugate base. That's got to be a salt. Or I could add in the base and its conjugate acid in a salt, right? So I could just take the two ingredients that I need and put them into solution together, make myself a buffer. The other option is that I could take my weak acid and add a strong base. Okay, so here's that first option. Here's my weak acid. And when I add in OH minus, I am going to convert some to the conjugate base, to CH3COO minus. Okay? And so then I'd have both. I have to be careful here with the mole amount of the strong acid and of the strong base and weak acid so that I don't overconsume and just make a really basic solution. Okay, then the other option would be I have some of the conjugate base and I convert some to CH3COOH, some of the weak acid, with a strong acid. Again, these types of preparations, you have to be careful with the number of moles so that you don't overwhelm it. All right, so I've got a couple, I think I've got a slide with a bunch of combos, and I want you to take a look at these and decide which ones will make a buffer. Okay? So using these two approaches, tell me which of the following would result in a buffer. All right, thumbs up if it's a buffer, thumbs down if it's not. First one, is that a buffer? No. That's just a really illogical way of making a salt solution, of making table salt solution. Okay, we're just going to neutralize our strong acid with our strong base. This is just a salty NaCl neutral solution. So no, that's not a buffer. How about our second option here? Is that a buffer? Thumbs up if yes, thumbs down if no. Good, that's a buffer. That's the most straightforward way of doing it. Here's my acid, here is my conjugate base. It's got to come as a salt because I can't just have a negative thing sitting with a bunch of other negative things. There's got to be that Na plus there to balance it out. But yes, of course, that makes a buffer. How about the next one? 3, is that a buffer? No, because you would catch that I'm adding acetic acid to the formate ion. This is not the conjugate base. Okay, so yes, that's a weak base, but it's not the right one. So no, that doesn't make a buffer. Hey, how about 4? Does that make a buffer? No, I'm adding a weak acid to a strong acid to make a really acidic solution, but no buffer. I don't have any weak base. I don't have the conjugate base here, so that's a no. All right, 5. Is that a buffer? Good, that is a buffer. This is the right way to do a strong base, weak acid. I have added in half the amount of strong base. So half of that CH3COOH gets converted into the conjugate base. So I will have meaningful amounts of both when I add those two together. That is a buffer. All right, last one. Is that a buffer? This is probably the trickiest one. That's a no. Why? Well, you're adding equal amounts of CH3COO minus and H plus. If that's a 1-to-1, I just have converted all of my weak base, my conjugate base, into CH3COOH. I have just made a weak acid solution. There's no base left. There's no weak base left because I converted it all. I could have done this if I had 0.5 moles of HCl. But when they're equal amounts, I've converted all of my weak base. Yeah. Say why is what? Why is it a buffer? Because I am just straight up adding HA to A minus. That is the conjugate base right there as a salt. No, that's a strong electrolyte. It's a salt that splits up into CH3COO minus and Na plus. That's the weak base. That's the conjugate base that I need to make a buffer. That's the only way to have that sitting out on the counter. I gotta make a salt out of it. All right, so now you are all experts at making buffers. Now we want to talk about which buffers we want to make, okay? There's two features of a buffer. There's capacity and there's range, okay? So capacity is just your ability, like how much acid and base can you neutralize, okay? This trends well with concentration. So the higher the concentration or the higher the volume, then you have a higher buffer capacity, okay? The higher the initial concentrations, the more it can neutralize. All right? So we are going to see that in action now. We are now going to actually do a buffer calculation. Okay? So not just, hey, I've made the buffer, but now I've made the buffer and I'm going to add some OH minus or H plus. We want to see it neutralizing that addition of acid and base. Okay? So your book splits this up into 2 steps. Okay? We have our buffer. We've already made it. Okay, then we add in strong acid or strong base. This first part is the stoichiometry calculation. We will do this part in BCA tables. And it's got to be in moles. Okay, where we're doing 100% conversion. We throw in some H plus. It converts A minus to HA, okay? So we change those equilibrium values because we're adding in OH minus or H plus. And then with the new values, then we go in and can do an equilibrium concentration, which will usually be a Henderson-Hasselbalch, okay? So that's our 2-step, okay? Our 2-step process. So let's look at that for 2 different buffers, okay? We're going to start with a 0.3 molar buffer, all right? So I'm sticking with acetic acid. I've made it, so I've got 0.3 molar of the acetic acid and 0.3 molar of the acetate anion, and now I'm adding something to it. I'm going to add in this 20 mils of 10 molar HCl, okay? So a lot of H plus. And I'm going to track how does that pH change. All right, so we got to do a BCA table first, which means working in moles. So first, work in moles. So I'm going to get moles of H plus. My volume, I have 20 mils, which is 0.02 liters, and it's 10 molar. It's pretty concentrated. So I'm really adding in 0.2 moles of H+. Fortunately, I've made this a very simple solution where it's just 1 liter, so I know that I have 0.3 moles of CH3COOH and 0.3 moles of CH3COO minus. Okay? So now I've got my moles. I'm going to go into the BCA table. BCA is just before and then change and then after. And we're doing it as a stoichiometry, so we're just saying like 100% of this reacts. When I put in that H+, the reaction that happens is we convert our CH3COO minus to CH3COOH. Okay? So before, I have 0.2 moles, 0.3, and 0.3. I'm just pulling those values from up here. My change, I decide on the change based on what the limiting reactant is. I have the least amount of H+. So that my 0.2, I'm going to use that as my limiting reactant. So I'm going to subtract 0.2 from each of my reactants. All of it gets consumed. But as that happens, I am then making 0.2 of my acetic acid. So at the end of the day, after this has happened, I have neutralized all of my H+. I have a little bit of my CH3COO minus left, and I have a lot more of my CH3COOH. Okay? So now I've got my values after we've neutralized our additional H+. So we're going to take that and plug it into our Henderson-Hasselbalch. Okay, so pH equals, I've given you the pKa, 4.74, plus the log, okay, of my base, which is now down to 0.1 over 0.5. Okay, in a Henderson-Hasselbalch, I can leave these in moles because molarity over molarity equals moles over moles. I don't need to go through the trouble of dividing by liters because I would do that for both. But yes, the volume is changing because I've added in 20 mils of HCl. But I can just grab those. If I'm going into a Henderson-Hasselbalch, I can grab those moles and put them in, and I calculate that my pH is now 4.04. Okay, so I put in a lot of H+. That's 20 mils of a really strong HCl solution. And my delta pH, my change in pH, okay? My original pH was actually 4.74 because those were equal in here. So my delta pH was negative 0.70. So, a measurable, but not an enormous shift or change in pH. That's because it was buffered, all right? Now, I want you to work on this. We're going to do the same problem again, but we are now increasing the buffer capacity. So you can use this completely as a roadmap, do this again, but now it's not into a 0.3 molar buffer, it's into a 1 molar buffer. So calculate the pH of this new buffer after you add in 20 mils of 10 molar HCl, and calculate delta pH. How much did the pH change for this solution? Okay, I'm going to leave this up just in case you didn't get it all down, but I want you working on that next problem. What is changing between these two? So the setup is entirely the same. You start off, you calculate moles. Okay? That hasn't changed for HCl. Okay? We still are adding in 0.2 moles of H+. All right, what has changed is now I have a lot more moles of my weak acid and weak base. So I have 1 mole of both of those. So when I go to write out my BCA table, I'm starting with larger values for those two. It's the same process. H+ is going to convert some of my CH3COO- to CH3COOH. But now I'm starting with a larger value in those 2 points, okay, in those 2 parts of my table. This is still very much my limiting reactant. So I've consumed all of it, and I will be left with 0.8 of my acetate anion and 1.2 of my acetic acid. Those are the numbers that then get brought into your Henderson-Hasselbalch. So 4.74 plus the log. And now, even though I added in the same amount of H+, because I started with larger amounts of my base and acid, their ratio hasn't changed very much. It started as 1 to 1, okay? And before it changed very significantly. It was 0.1 to 0.5. But now we have that change has lessened because we have a larger buffer capacity. So the pH is now only 4.56, and our delta pH was only negative 0.18. So higher buffering capacity, smaller change in pH. It's better at neutralizing. It's more capable of neutralizing that H+. Same story if we had put in OH-. When we have this larger capacity, I should see a smaller change in pH. So I want to put this in perspective just to drive home how significant this is. All right, so there's our calculation for the 1 molar buffer, okay? But when we did it, so for 0.3, I'm just pulling the numbers. Our delta pH originally was negative 0.70 for our lower capacity. We just did it for the higher capacity. That was a delta pH of negative 0.18. And then I'm going to compare it to what if I had just had pure water starting at a pH of 7, and then I added in 20 mils of 10 molar HCl. That would have started me at pH of 7, because that's just pure water. Okay, and if I had then put in 20 mils of this 10 molar strong acid, that would have given me an H+ concentration of 0.196 molar, and the pH of that would be, where are you? 0.71. So without a buffer, putting in that H+ would have moved us from pH 7 down to a pH of 0.71. So 6.3 units of pH change. And when we did it with a buffer, it didn't even reach 1 unit. So buffers work. That's just right. Buffers work. Okay, and we just proved that to ourselves, right? Down here, if it was not a buffer, so not a buffer, our pH change was negative 6.29, an enormous change. That same HCl had limited impact for our buffered solutions, okay? That's what I want you to take away from this slide, all right? So that's buffer capacity. This is hold this in your heart, find a nice cozy place for it, because we are going to use, what we've been doing is basically titrations. Everybody loves titrations, I know that, and we're going to do more of them on Thursday. So this work is this BCA table going into an ICE table or a Henderson-Hasselbalch that's coming back. Okay, so it's going to build on itself. The last point for today is let's talk about buffer range. Okay, so the pH range of a buffer. Buffers don't work for any pH. They only work over specific pHs. All right? So what is that range? Okay, so we need to have amounts of HA and A minus. That's our requisite. That's what we have to have, both of them. Okay, if we're gonna buffer in either direction. So if we look at in our Henderson-Hasselbalch, the ideal buffer is when we have equal amounts of acid and base. Okay? So that would be the log of A minus over HA when those two are equal. In other words, that would be the log of 1, which is 0. So we want the best place to use a buffer. Okay, we want to pick a buffer that the pKa of the acid is equal to the pH that we want to work at. Okay, so we've been doing these acetic acid buffers. Okay, that works around 4.7 pH. If I wanted to do biochemical work, I would not use an acetic acid buffer because my blood is not pH 4.7, it's 7. So I couldn't use an acetic acid buffer because it doesn't match the pH that I'm interested in. That pKa is wrong. Okay, so the point I want you to take home from this slide is that you have to pick the right weak acid. Okay, you need the right pKa for the right pH. Okay, so here's this example. We've been looking at our acetic acid. It is equal 50-50 at 4.74. As I deviate from that, okay, once I get down to 2, if I had a pH of 2, I'd have 100% CH3COOH. That's not a buffer anymore, right? That's just a weak acid, okay? I have to stay in that range where I have meaningful amounts of both, okay? So I have to stay here. If I want to use this buffer, I could probably work from 3.7 up to 5.7. That would be an acceptable range for an acetic acid buffer. All right? So again, if I can't use this really for biological systems. So I'd go back and I'd look at my acids and I'd say, which one works? Which one's around 7? And I'd say, hey, carbonic and phosphoric acid, those are options because they have pKa's near my desired pH. All right? So that's range. We will pick up there on Thursday.